Hi, my name is Sophia Lin. This is Lab 1, Constant Velocity. The purpose of this lab was to observe and analyze the motion of some object that is moving at the same speed without changing direction, construct a model that accurately describes the motion, then compare it to a predicted model using GlowScript and computer data. The main model I used in this lab was a position versus time graph, and on that graph I included both the observed and predicted motions, which allowed me to compare and contrast them. The fundamental principle used was Newton's first and second law, which with enough rearranging gives you the kinematic equations that can describe the motion of our object. In the end, I found that the slope of my observed object, which was a spool of thread, was less than the predicted value. The first fundamental principle used was Newton's first law of motion. An object at rest stays at rest, and an object in motion stays in motion with the same speed in the same direction unless it is acted upon by an unbalanced force. Thus, because in our lab, our object should be moving at a constant velocity, same speed and direction, we can assume that the net force is zero. Newton's second law of motion relates the net interaction between system and surroundings to the observed motion, which is the change in momentum of the system. Because we know net force is the change in momentum, we can integrate both sides to get the updated velocity kinematic equation. Once we found that equation, we can then use the fact that velocity is equal to the change in position. Thus, integrating both sides and plugging the updated velocity kinematic equation, we can then get the updated position kinematic equation. These two equations are used to model the motion of our object. To do this experiment, I first filmed an object on a flat surface rolling in a straight line, and in this case it was a spool of thread on a table. After, I imported that video into Tracker, added axes, and calibrated my video. I then added position values at the center of mass at various points in the video, and then was able to extract the data points as time and position coordinates, put it into Excel, and was able to create a graph that represented the motion of the spool of thread. Here's a quick little video to demonstrate that. The system of this lab is a spool of string, and we can assume that there's no air resistance, friction, gravity, or force applied to the object. The initial position I found from the tracker was 2.34 e to the negative 4 meters, and the initial time was 0 seconds. To find the initial velocity, we used 2 points from the tracker data in using the equation final position minus initial position over the change in time. We got 0.43 as our initial velocity. Here is what my graph looked like, with time being on the x-axis and position being on the y-axis. We can see that it is relatively straight, but there's obviously some imperfection. To find the predicted data, I used GlowScript, where we plugged in the initial position and velocity found from the tracker, with the initial time being 0 seconds, initial position 2.34 e to the negative 4, and initial velocity being 0.43. I then set force equal to 0 because of Newton's first law, which was explained earlier, and used the position and velocity equations found earlier from Newton's second law, and plugged in 0.1 seconds as delta t to match the intervals of the tracker. Here is a graph that compares the theoretical computational data in orange and the observed data in blue. We can see that the blue begins to taper off and become less than the predicted. Thus, it can be concluded that our system was not moving at a constant velocity, so some outside force had to have been acting upon our system. This can be because of many things. The first, and probably most likely, is friction. Most likely, the table provided a force against our object, thus slowing down the system. This error can also be due to human error, where we're not placing the tracker's points perfectly in the center of our object every single time, as seen in the photo in the left. Our video was also filmed at an angle, thus, because of the difference in perspectives, could also be the reason why our data is slightly skewed. If our axes were to be flipped, i.e. the positive x-axis becomes the negative x-axis, everything would remain the same. However, our slope would just be negative, but our magnitudes and everything else would have remained equal to the observed and predicted models from our lab. Now, is it possible for us to say how many pushes and pulls are added together to give zero net force in the case of our observed data? It's not, because there are other forces acting upon the object once our object is in motion. There's frictional force, air resistance, and other forces that just weren't considered when we were taking our observational data. This is probably why our graph shows a difference in the theoretical and observed model. Thus, in this lab, we learned how to observe and analyze an object moving at constant speed and direction, compared it to a theoretical and predicted model, and identified the errors that could have explained the deviation in our model.